I'm Supreeth. I'm an engineer at Yahoo. I'll be presenting a problem that we solved for our display ads attribution within Yahoo. I'm part of the data team. What do I expect you folks to take away from this session? There would be a framework which we'll present, and it will have a pattern. I would appreciate if you guys can concentrate on the pattern, because I think that's applicable across the industry, and that might be a good takeaway. We can take the questions at the end, and we can get started. Okay. The agenda of the talk is going to be like the following. We're going to have a problem description where we I'll try to introduce you all to the problem space, the domain, what we are trying to do. Then I'll try to generalize the class of problems, and maybe some of you guys can relate to what you have in your workspace. Then we'll talk about our framework, which we'll present with a pattern, which might be interesting. And then we'll do a performance comparison to existing methodologies. And finally, we'll go to the conclusion. So in Yahoo, we have a lot of users who come to our websites. And when they come to, when you actually end up typing a Yahoo page on the browser, the request goes to our web server. So how many of you are aware of how many of you are familiar with how the ad system space work? Okay, I see a few hands. But I'm going to spend some time on this. It might be a repeat for some of you, but it'll make the problem space relevant for the folks who are not from advertising. So when a request goes to an ad server, the request goes to a web server. In the backend, the web server makes a call to the ad server to get the relevant advertising information. And the final payload is delivered back to the user on the browser. What we see here is there is a variety of events that are generated in the backend, and some are generated at the client side. So something happening with the slides. Yeah, thank you. So the ad server, when it returns back an ad, it is also going to put in a log for the ad that it returned, which we call in this context as a serve event. A serve event has the complete context of an ad. So it would have all the details that the ad server knew about the ad. When the ad gets displayed on the browser, there are going to be client-side events, which we are calling it as impressions, clicks, and interactions. So what is an impression? An impression is just proof that the ad got displayed on the browser. So when you go to yahoo.com, and when you see an ad on yahoo.com, it means that since you have seen the ad, there would be an appropriate impression event that gets generated. We strive hard to keep the performance of the page load to the best, which means the total payload that gets delivered on the browser should be as small as possible. So that means that the client-side beacons, we always try to keep it to a few bytes. The complete context is always from the server side, which is the serve event. Why is this designed in a way wherein we are keeping the context on a backend and the client is having only a few bytes, and why are we doing all this? So this is needed because the proof of an ad being served on the browser is important for us to attribute back to our accounting system, our budgeting system, our research. So we just cannot take the proof that an ad got served from the ad server. That is not just sufficient for us to do a lot of analysis. We would ideally want to join whatever we get from the client side to what we emitted from the server side to make the complete sense of the picture. That is the reason why we have built a system on these lines. So let's look at the need for attribution. Uh, Typically, once the serve gets delivered from the ad server side, after a few seconds, you would expect that the ad gets shown on the browser and the impression event comes in. But that is the typical scenario. However, there are cases which don't fall into this scenario. Uh, you might have had your page open, web page open on your browser, and the next day you might come and click on it. That's one scenario. So you would want to still capture the event that you clicked on it later. Or you might have some network delays, which means that though the Yahoo ad server said that it delivered the serve now, it would actually reach the browser after some time. There might be delays. So the business requires us to take an impression or a click which is coming on the client side and then go ahead and join it with the server side event, which is the serves. And this might be from several hours to days. We would want to go back and attribute a client side event back to a server side event. How important is this for Yahoo? So this is really important because this is behind our entire display ad revenue system, which means that whatever we are presenting here today is actually part of a system which is delivering more than a few $1 billion of revenue. We also have to do this in a very low latency. So we strive hard to get this done within 5 minutes because of business requirements, which means we have to take an impression or a click that is coming from a client side and attribute it back to the serve event, and this entire process has to be done within a 5-minute batch interval because our business needs it. So let's look at the distribution. So what is this graph? So this graph is trying to tell us that given an impression, it goes back to see how far back do you actually have to look back to get the serve. So as you might see here, for the impression scenario, which is the case of an ad being shown, most of the impressions get shown in the same interval that the serve got emitted. So the impression and the serve are very close to each other. However, there is a small there's a tapering scenario here, and as you go back in time, the number of impressions that match back to the serve might be very, very minimal. However minimal it is, we still need to match it. The attribution still is very relevant. The scenario changes to a large extent with the click scenario. So in case of click, the user might not immediately click on the ad. So the user might actually see what the ad is about, or sometimes there might be an animation on the ad which might make the user click on the ad a while later. So all of these have to be captured, and this is typically what we see in our production systems. So what are the general class of problems that we are trying to solve here is we are trying to do a sparse join where one side of the join is a few hundred megabytes or a GB or so, and the other side is very huge. It's today in production we are seeing close to 5.5 terabytes. And the business requirements actually kind of mandate us to do an outer join. So if the impression or the click did arrive, we have to attribute it back. Even if we can't find the serve, it still means that we need to use the impression or click in our processing. So it's kind of an outer join on the smaller data set. So that's the generic class of problems. Where do we see this problem relevant? So if we have to attribute back a video event, so there is a video interaction, there is a click, there are some pauses, there is some plays on the video, and you're trying to attribute it back to some activity data on the back end. This is certainly relevant. We have seen within Yahoo that we have a similar problem on our audience view click interaction. So when the web server is giving out a page, so the page might have other attributes where we want to do some investigation. In a generic sense, if there is a client beacon, which is very small, and you have a server-side event, which has a lot of context, and you want to somehow annotate the client event with the server-side event, where the scenario is where the scenario is more like a sparse scenario, this problem set does apply. So that's the generic class of problems. So we did try a lot of existing join strategies in Pig and MapReduce, and some of them I've listed here. So the first one being the merge join. To do the merge join, we actually had to sort the data set, and that was extremely costly in our case. So we tried that, and we found that the performance cost was very high. We tried the hash join, but the hash join introduced an inherent shuffle, and the reduce phase was also taking a lot of time. We did try the replicated join because that kind of fits the problem statement, but the replicated join did not meet our performance requirements. And lastly, to do a left outer on the replicated data set it's not possible in a replicated join. Lastly, we did look at the skewed join, but our data set is not skewed because of the kind of keys that we use. So it did not actually apply to our scenario. So this is the problem statement we are trying to solve. We are trying to achieve a sparse outer join on a very large data set with high performance requirements. And we want to do it on the grid because we have invested heavily on Hadoop and Hadoop-based technologies. Let's spend some time on the attribution framework. So what we are trying to do, or how we are trying to solve the problem, is we are using some smart instrumentation strategies which help us do the sparse join better. We'll talk about our aggressive partitioning and partition pruning strategies, how we actually achieve what we want to achieve here. And lastly, we have a different join query plan, which is making the join partition aware. It is making it more efficient than whatever are the current joins that we have. So we instrument for attribution. So when we looked at this problem, we needed to build in hooks into the client event such that we could go back to the server-side event and attribute it back. Just using a timestamp was not sufficient. So you just could not take an event and go back and start looking. So what we did is we used a server GUID, which is a global unique identifier of the serve event, and we used the small, it's a few bytes. So we used that within our impression or the click event to just, whenever we got an impression, we also got the server GUID or the serve that corresponded to the impression of the click. We used other clues for partitioning. An example is, I've given an example of a timestamp, but another example is if you have an advertising ID or a campaign ID that you're associating with your advertisement, which doesn't span the complete time interval, you can use that for doing partitioning because it helps you get efficient physical partitioning on the disk. We use partition keys effectively in all the event instrumentation, both on the serve side and on the client side. And in this example, I don't have a marker, but so if you see the serve, there is a serve GUID, which is a serve unique identifier, and we have the serve timestamp and the other context of the serve, which could be a lot of fields. It's not just one field, it could be many fields. However, on the impression, we use the same serve GUID when we deliver the impression, and we use the same serve timestamp as a clue. So this is an example of an instrumentation which we are doing so that we can only do the join. So we are kind of instrumenting to do the join. We tried a lot of partitioning approaches. In the end, we kind of went with a kind of a mixed approach where we do hash partitioning on the join keys, but we do range partitioning on the timestamp. So we kind of mix both hash and range, and it's like the hash key that we build is built in such a way that we get uniform distribution. We have tried hash FNV, and we can try murmur, but in production we use hash FNV because this combined key is more of a string, and hash FNV gives us a very good distribution. So once we do partitioning, it creates a lot of partition, and depending on how aggressive your partitioning strategy is, the total number of files keep going up. So we actually need to prune. So when we need to prune the partition, we use the same keys as clues. So the first clue that we use is we use a timestamp, and we eliminate all the range partitions that don't fit into our use case. And once we get to the right partitions based on the timestamp, we then use the hash partition key to do further pruning so that our I/O costs are very, very little. The framework allows configurable partitions both for the left side of the join and the right side. That is the data set which is a little smaller and the data set which is bigger or in a few terabytes. Depending on how aggressive one gets with the partitioning, the I/O costs vary. So if you partition very well and you can prune very well, the total I/O that your MapReduce job is finally trying to read is very little. So it has a direct correlation with that. Once we do the instrumentation, we got the partitioning right, now we've done the pruning. The next step is we had to do this outer join. So the outer join is not possible in the scenario that if you just use a replicated join in Pig. So we kind of use a smart join query plan. So here if you see the darker color, the darker purple, it's the data set that is in memory. So first we load our impression. Is the darker color visible to all of you? I just want to, okay. So first we load the impression event or the client-side event in memory, and then we stream the server-side event, which is a larger event, and we do an inner join. Once this join passes, we take the output of this, and that we are calling the annotated impression. Now we load the annotated impression again in memory. So the number of records in the darker boxes here is always small because it's representing the smaller data set, and that kind of fits into your memory. And the larger, the lighter color, those are the larger data sets. So the first time we are streaming the serve partitioned events, and in the second phase we are streaming the impression event. And since we are able to stream the complete impression event, we can do a left outer on the impression. Because in a replicated join scenario, if something is in memory, you cannot do an outer join on that data set because you don't know which other replicated instance will get the record that it's looking for. This is how we do the complete annotation, and we finally get the annotated impression. What is also interesting here is since we have built-in partitioning in the very first phase and all the way through, we can do this join in a partition-aware manner. So for every partition, we can have this join query plan, which means it gives us further more parallelism, and it helps us exploit and get to the low latency requirement very well. The attribution framework has a few capabilities which have been listed here. So we can do an outer join on the impression, click, or interaction, which means as long as the impression, click, or interaction exists, we will get an output record. We can do a complete annotation with the serve. If the serve has duplicates, we have also built into the framework a configuration which can help you do distinct joins on the serve. So you can say, I want to eliminate duplicates on the larger data set when you get the output. We can achieve sparse joins because we end up pruning a lot of partitions, and how far back you go doesn't have an impact on performance because your effective partitioning is deciding what is your I/O cost. And we effectively exploit the map side join that can be done using Hadoop and Pig. So in our implementation strategy, we use the Python embedded Pig heavily because that gives us enough hooks which helps us put in configurations and which gives us the Turing capability, which helps us do the partition-aware join. We can spawn the same job for multiple partitions very easily, which is not possible in Pig as is. We have built in a dynamic partitioning algorithm, which will allow you to configure partitions on the left side and the right side. And it associates a partition on the smaller data set with the partition of the larger data set and kind of keeps the mapping. So you can have your impression data set partitioned by 32, as in there are 32 partitions. And you can say the serve is very large, so I will go with 1024 partition. So it can manage all this. And lastly, the framework gives out a few configurable parameters which you can use to play and kind of get a trade-off. In the next few slides, we will spend time on what are the tuning parameters that the framework provides and what are the trade-offs that if somebody is using this has to go through. So the first parameter or the first configuration is the total number of server partitions. So as the total number of server partitions goes up, we can prune better, which means that our I/O cost is going to reduce drastically. However, the downside to this in Hadoop 20 and the systems before Hadoop Next is that the namespace keeps going up. And in some of our grids, we have seen that namespace is also a constraint. So depending on where is your infrastructure or how loaded it is, one can choose between these two trade-offs. That is, you are trading off between the total I/O versus the total namespace that is being used in the framework. The second parameter, which kind of plays into the total number of mappers versus the time taken for each mapper, is the split size. So if you want a map task to run for a longer interval versus if you want a map task to run for a smaller interval, but you have larger number of map tasks, you can play around with the split size. So as the split size keeps going high, that is, if you go to a split size of 4 GB or so, then what you see is the total time taken by the map task would be very high. However, the total number of mappers would come down. It's kind of intuitive, but by giving this as a configuration entry into the framework, it kind of allows you to do these trade-offs. We compared our framework with the other pig joins, and more importantly, the hash join in pig and the replicated join. You might see that the look-back period is slightly varied across all the three comparisons. The reason why it's varied is we also have to look into the other performance constraint. So for the hash join, we used a look back of just 8 intervals or 40 minutes. And the total I/O read was 180 GB, but the time that it took for us to complete was close to 43 minutes. Now this was the best case scenario. We could have tried for more look back instances, but on our production clusters, it's like we've already started hitting 42 minutes to run a 5-minute job, which is not scaling or it's not helping us. The second join that we tried was a replicated join. We went to around 5 hours of look back on the serve, and we could get it done in 7 minutes. But for any higher look back, the total number of mappers kept going up. And because of the isolation that we use in our capacity-based scheduling, it's very difficult and it's taking cycles to get it executed, which is not very efficient. With the attribution framework, we used a partitioning strategy which made the effective I/O just around 1.1 terabytes, and we could achieve this entire result in 6 minutes, which was kind of okay for our scenario. What is also important to note is you can, if you're not constrained by namespace, you can really get aggressive on partitioning. As in you can have partitioning mechanisms which kind of reduces I/O further, and you can only pick the partitions that matter to your client-side events. So we can even get better once we go to Hadoop 23 and the likes. So I have 3 conclusions here. The first one is this applies very well for a sparse lookup problem, and which has very low latency but high performance kind of needs. Effective partitioning or very aggressive partitioning will aid longer lookbacks, and it will reduce the total I/O cost. The levers in the framework allow you to trade off between the total time taken for a task versus the total number of tasks, or the total I/O versus namespace and the likes. So it's giving you enough levers as a person who's running the framework to try out different parameters and optimize for different parameters. We have a few things planned in our future steps. We want to try and load our entire serve data on HBase or Cassandra. The problem here being we have to run this every 5 minutes, and every 5 minutes we have to kind of look at 6 terabytes of data. So we have had some experiments there, but we don't have any conclusions to share at this point. We want to try to do an index format which kind of exploits the Bloom filter capability. This could be like a new format to do these kind of joins. And lastly, the same framework can work on Hive as well. We haven't built that, but we have just built for Pig. But as long as the 3 steps are followed, we can build a similar strategy on Hive. I think at this time, we can take some questions.
Can you explain your partitioning strategy a bit more? Like, do you first prune by time range and then by GUIDs, or the other way around?
Yeah. Can we go to the... So this is not in sync with the display, so I need to press and the person actually presses. There is a delay. So can we go to slide number 4? The slide before this, sorry. Thank you. So what we have done is we take the serve event, which is a few terabytes, and then we partition it by timestamp. Timestamp is a natural partition key that comes in. But once we partition the timestamp, we have split it into 5-minute intervals. Let's take that as an example. Now within the 5-minute interval, we create a composite key, which could be, in this case, it's a serve GUID and the serve timestamp. And this composite key, we do a hash and do a hash partitioning within that 5 minutes. So you built a range partition on the timestamp, and then you go ahead and build a hash partition within each range so that you can partition further. We apply a similar strategy on the smaller data set, which is a few hundreds of MBs to GBs. Did that answer your question? Any other questions?
So if you had a look back of, say, 24 hours, you would like do that join plan with all the 5-minute buckets going back up to 24 hours.
Yes.
And so how many mappers per bucket is that?
So that depends on how many partitions that you have, because it's a direct relation with the total I/O. So if you do a look back on 24 hours, you're actually looking at 288 instances of your 5-minute batch. And within the 5-minute batch, depending on how you have done your hash partitioning or how aggressive you were, you pick only the partitions that matter. And the number of mappers would depend on that scenario. In our case, we have had around 5,000 mappers for the parameters that we chose.
Regarding the number of partitions, did you have any constraints in terms of other use cases? So, or is this sort of is this a partitioning scheme built for this use case, and then other use cases are working on different clusters, or?
So we tried with 16, we tried with 32, we kept to powers of 2 so that the mapping is very easy and you can map back. The constraint that we saw is the namespace. So on some of the clusters that we run, we have quotas to guarantee isolation, and due to that, the namespace is constrained. And whenever the namespace constraints are kind of on our, it's like saying if you're running out of namespace because of other things that are running on the cluster, we kind of reduce the partitioning and we kind of take in the cost of I/O. However, if the namespace is free on the cluster, we just configure to make sure that we exploit and the I/O costs come down. It's a trade-off.
Okay.
So how would this have changed if the data were skewed? What would you have done differently?
That's a very good question. So the keys that we introduced on both during our instrumentation, we kind of made sure we introduce keys which will help us avoid the skew problem. However, if the data is skewed, then you can kind of put in a skewed join on top of this framework and try to see how you can. So in the second stage of the join in the query plan, you can kind of use a skewed join. That might be a thought, but we have to prove it through experiments and see if that's the right approach. Are there any other questions? I think we have few more minutes. Okay, thank you all for taking time. Thanks.